Hey everyone, Mr. Newman here, and today we're going to learn about limits at infinity. So this is a short video. First of all, I want you to notice this function, f of x. Here's the graph of it. That's the black curve, both the bottom left and the top right. You notice it's a rational function. And also notice it has a horizontal asymptote at y equals 1/2. So we're going to locate these two limits on the graph and evaluate them. First off, notice our limit is as x approaches negative infinity. What that looks like is x going all the way out to negative infinity, going on out forever. And the question is, what is the y value as x gets closer and closer to negative infinity? Or, well, not really closer, but just keeps going out towards negative infinity. What does, if anything, what does y get closer to? Well, you notice since there's a horizontal asymptote at 1/2, then the y value is getting closer and closer to 1/2. So the limit as x approaches negative infinity of this function is 1/2. On the right, the x approaching infinity goes all the way out to the right forever. And so the question is, all right, what's the y value getting closer and closer to there? Well, again, because there's a horizontal asymptote and it's the same asymptote, then this value is getting closer and closer to 1/2. So that's great if we have a graph and we can see it clearly like this, and I tell you the horizontal asymptote is this. What if I just give you an equation? Now, one thing is you could go back to, remember in rational functions, how do you find the horizontal asymptote? And we're actually going to look at something similar to that, but there's a quick way to calculate it algebraically, and I'm going to show you that way. The thing you have to know is that when x approaches positive or negative infinity, the most important term in a rational function is the highest power. So these are horizontal asymptotes that we're kind of look at, all right? The highest power is the most important term. Why is that? Well, the reason for that is because if you think of really big numbers, x to the 6th of that really big positive number is much more than x to the 5th. And x to the 5th is much bigger than x to the 4th when x is really big. And so that double greater than sign just means really greater than. Same with that, x to the 4th is much greater than x to the 3rd. And that goes in both directions. So the highest power, we call that the degree, of the polynomial is the most important term. So what we're going to do for our rational functions, we're just going to look at the degree, the highest power. So let's do that here. We have three situations. The first is when the degree of the numerator is greater than the degree of the denominator. Here's an example of that. Notice how x to the 5th is greater than x to the 4th, and x to the 5th is in the numerator, so 5 is the degree of the numerator. Well, what happens when you plug in really big numbers as x approaches infinity? That numerator, the top, is going to be much bigger than the denominator. It's going to give us a graph that looks like this. It's going to just keep growing, okay? That means that the limit does not exist because it doesn't approach a specific number. It keeps on going up and up, or down and down forever. So if the degree of the numerator is greater than the degree of the denominator, the limit does not exist. What if the degrees are equal? Well, if the degrees are equal, like in this situation where x squared is 2 is the degree of the numerator and 2x squared, 2 is the degree of the denominator, what is important then is their coefficients. Because x squared on top is going to grow at the same rate as x squared on the bottom, those two numbers are always going to divide out. In fact, nothing else matters. We could cross out all the rest of the numbers behind it. The only numbers that matter, the only terms that matter are the x squared on top and the 2x squared on bottom. So it's actually, we get a horizontal asymptote at the ratio of the leading coefficients. What do I mean by that? Well, look at the leading coefficients. That's the coefficients on the highest powers. On the numerator, that's a 1, and the denominator, that's a 2. Those are the numbers that are going to be left over once those big numbers divide out, the x squared on top and the x squared on bottom. So we know that there's going to be a horizontal asymptote at 1 divided by 2, or 1/2. That means the limit is going to be 1/2. Pretty nifty, huh? Let's look at our last situation, and we'll do some examples of these in just a moment. The degree of the numerator is less than the degree of the denominator. this situation here where 8 is in the denominator and 5 is in the numerator, well, if the denominator is way bigger, because the degree on the denominator is bigger, then that number is going to get closer and closer to 0. There's going to be a horizontal asymptote at x equals 0. And so the limit as x approaches infinity is going to be 0. Now, if these three situations look familiar, it's because we talked about these exact situations when we discussed horizontal asymptotes back in rational functions. So we're just talking about this in a more formalized term where we're saying as the limit approaches, as x approaches infinity. All right, let's do some examples. In this first one, I'm looking for the degree. The numerator is 1, the denominator is 2, so the denominator is greater. That means that this is going to approach 0. So the limit as x approaches infinity is 0. For the next one, notice that we have 2 is in the degree of the numerator and the denominator. So the only thing that matters are those leading coefficients, -2 and 3. So there's a horizontal asymptote at -2/3. That means that's the limit as x approaches infinity. For the third one, the 3 is larger than the 2, so the numerator degree is larger than the degree of the denominator. That means that the limit does not exist because that number is going to actually keep getting more and more negative because of the -2 on top. Okay, let's come down here. It gets a little bit tricky here, but one of the things you have to know is that the limit of two numbers is the same as the limit of the first number, plus or minus or multiplied or divided by the limit of the second number. So right here we can say the limit of this, that right side, 3 over x squared, that's going to be closer and closer, get closer and closer to 0. So the limit of that is 0. So the limit as x approaches infinity of this expression is equal to 4 minus 0. Well, that's just 4. So that is the limit of that entire expression. Notice how we eliminated one the fraction because we knew that gets closer and closer to 0. If that fraction got closer and closer, if it blew up, if it got way too big, that would obviously overpower the 4, so the limit would not exist. For the next one, the limit as x approaches -infinity, I'm going to look at the degrees. Notice the degree in the denominator is 2 and the degree in the numerator is also 2. So we need to look at the leading coefficients, but we have to be careful and ask what are the leading coefficients. The numerator is -1 because that's the number in front of the x squared and the denominator is 1. So it might help to write it in standard form if you're wondering why is that -1. Well, -1 divided by 1 is -1, so that is the limit as x approaches infinity. For the last one here, I'm actually going to write this out, so then I'm going to put the numerator in standard form, -x cubed plus 4, and the denominator I'm going to square out. Well, once you write down the very first power, you actually don't need the rest of this stuff, but I'm going to go ahead and leave it there anyway since I multiplied it. All we really care about are the 3 and the 2, and that means the numerator is a higher degree than the denominator, so this limit does not exist because it's going to get much larger, or rather more negative than the denominator. One last thing I want you to notice is that for those last two problems, the limits were approaching -infinity, but the situation remained the same. The only time that would matter is if we had something like an absolute value where it mattered whether we were positive or negative. But for the most part, all the situations where x is approaching infinity are the same as when x is approaching -infinity. All right, thank you very much for watching.